right, so let's look at the answers to the toy truck activity. So in going through that toy truck activity, remember that when we had the toy truck going across the surface, it took, let me get my thing out, according to the lab sheet, it took 2 washers to get it going across the table, all right? And then when we weighted the truck down, when we put the brick on top of it, then it took 35 washers, according to the lab activity, to get it to go across the table. Then we did the little short incline, 1 book, and it increased my empty truck to 10 washers to get it to go up the table. And when we weighted it, when we put the brick on top of it, then according to what it's on there, it took 67 washers to get it go up the incline. That was the short incline, the low incline. Then the high incline, which was 2 books, it took 25 washers to get the truck to go up the incline, all right, when it was empty. And it took 125 washers to get it to go up when the brick was sitting on top of it. All right, so that's the data that I gave you online according to this activity. So when we look at the questions, all right, oh, and then also it was the whole idea, how many washers did it take in order to get it rolling? I know when I did it online, it took a little bit less, all right, but according to what was written down for you, it took 22 washers to keep it rolling up the incline, all right? And when I did it in the video, it took 12, and it took 13 to get it rolling by itself, but it took 12 in order to keep it rolling. Either way is fine with me, all right? So now let's look at the questions. Number 5, what happens to the amount of force needed to make the empty toy truck accelerate on the flat surface versus the 3 centimeter incline versus the 6 centimeter incline? Well, what happened to the amount of force? That force went up. It got greater and greater trying to get it to go up that hill. All right? It took a small amount of force to go flat, a little bit more force to go up, and a whole bunch of force to go on a really steep incline. So it takes more force in order to get it to go up a steeper incline. Question number 6, what happens to the force needed to make the weighted toy truck go on the flat, the low incline, and the high incline? Same scenario, right? It takes more force because there's more weight. But as you increase that incline, it takes more and more force to get that toy truck to go up the incline. Question number 7, how does the amount of force needed to accelerate the empty truck compared to the weighted truck in all the tests? Right? Well, the empty truck takes way less force because it doesn't have as much mass to it. Oh, look at it here, mass and acceleration, how much force. Right? That's what this relates to. So when we put the brick on top, we added a whole bunch more mass, so it's going to take a whole lot more force in order to accelerate it to the same amount of speed, or just get it to accelerate. So the more mass, the greater the force in order to make it accelerate. All right, question number 8. Now look at the data from number 4 above when you were finding out the force needed to keep the truck rolling compared with getting the truck rolling. Okay? On that, notice it took less force in order to just keep the truck rolling than it does to have it sitting still and get it to start rolling and get moving. Right? And this is why inside of our cars, I want to say highway gas mileage is better than city gas mileage on a car. When you go out and buy a car, they're going to give you 2 pieces of data about the gas mileage of the car in city and gas mileage on the highway. Highway, they do better because once you get the car rolling, it doesn't take as much force to keep the car rolling. So you don't burn as much gas. Right? But when you're in the city, think about the idea, well, you get rolling, then you come to a stop sign, got to stop. Right? Then you get rolling again, come to a stoplight, got to stop. Right? Then you get rolling again, you got to turn up ahead. So you slow down, and then you got to speed back up. And you're constantly slowing down, speeding up, slowing down, speeding up, stopping, starting, stopping, starting. And every time you do that, it takes more energy in order to get that car rolling again. So your gas mileage goes down. Right? As long as we can keep the car rolling all the time, then we get better gas mileage. That's one of the ideas behind the idea of the roundabouts, because we can actually, if there's no cars coming, I'll remind you of that. If there's no cars coming, then you can roll through and go into the roundabout. If there's cars coming, remember you got to stop, let them go first that are in the roundabout, then you can pull in. But again, if there's no cars, then you can keep rolling, and it will increase the gas mileage of your car. Besides the idea that it's safer than having the stop signs at intersections. So. All right, so it does take less energy to just keep a car rolling than it does to make the car get rolling. Question number 9, how does this activity relate to Newton's second law of motion? Yeah, there it is right behind me, force equals mass times acceleration. Right? So as we raise the mass, it takes more force to get that object accelerated. Right? If we lower the mass, if the mass becomes less, then it takes less force to get the object accelerated. All right. So number 10, how do you know that the non-moving truck in each test had inertia? Remember, inertia is the idea that that truck wants to do what it's doing. If it's just sitting still, doesn't want to stay sitting still? Yes, because we had to drop washers in there in order to get enough force to finally get it to go and start to roll. Okay? So the truck does have inertia, and the idea that it's resisting motion, right, until we get enough force into it to finally get it to start rolling up the hill or roll across the table. So it's the whole idea, we got to get enough force into it to make it go. All right, well, there's the answers to the truck activity. So we'll see you next time. Have a great day.